Hi guys, today's video is going to be talking about Newton's third law. So while the first two laws have very obvious applications, the third law is a little bit more of a conceptual law. So it's going to come up a lot in trying to set up these problems, but it might not come up as explicitly as the first two laws. So first of all, let's talk about what it says. So the third law tells us that when two objects interact, they're both going to exert a force that is equal in magnitude and opposite in direction on each other. So one huge misunderstanding which comes up a lot is that these, what are called third law pairs, which is this equal and opposite forces, never act on the same object. So whenever you're dealing with Newton's third law, you're really implicitly dealing with two separate objects. And so for instance, if you draw a free body diagram, the third law pair must be acting on two separate objects in that free body diagram. So this is a really important point to understand, because if that weren't the case, if a third law pair ever acted on the same object, we know by definition they're equal and opposite in magnitude, then they would just cancel each other out on that object, and basically motion would be impossible. We would have no way of getting a net force, because every force we exert would have the opposite force. If they acted on the same object, that object would just never move. So it's very important to understand this, and so we can see this in a simple example where we just look at a table, which I'll just draw simply here, and we have a book. So I'm going to draw this book here as a box. And so we have a table and a book, and we know the two forces acting are going to be a normal force and a gravitational force. And these are the two forces acting on the book. So a question we can ask is, what are the third law pairs here? And so one answer that students commonly give is that the normal force and the gravitational force must be the third law pair. And that's not true. So in this case, the normal force and the gravitational force are equal and opposite, so that's true, but they are not a third law pair because they're both acting on the book. So it's important to remember that. If it's acting on the same object, it is not a third law pair. So if we want to realize what the third law pair to the normal force and the gravitational force are, we have to think a little bit about the interactions that those are feeling. So one way to figure out very easily what a third law pair would be is to rewrite something like the normal force as the force of something on something. So this normal force, I would rewrite it, or think about it in your head, as the force of the table on the book. So if that's the case, to find the third law pair, we just flip those words. So in that case, the normal force is the force of the table on the book, and therefore the third law pair will be the force of the book on the table. So again, if we drew the third law pair, that would really be acting here on the table. That would be our third law pair. F of B on table, let's say. Book on table. But again, realize this is acting on the table and not on the book. So we have to keep that in mind. And then the gravitational force is a little bit trickier, but it's the same idea. If we want to rewrite what the gravitational force is in terms of F of blank on blank, we would call it the force of the earth on the book. Really, it exists because the earth is pulling the book downwards towards it. And so therefore, the third law pair is actually being exerted on the earth, right? We can imagine this is the earth. The earth is actually feeling a force of the book on the earth. And that's to say that the earth is technically pulled up by the book. The earth is so much more massive, of course, that we don't see the earth moving because the book exists, but that force does exist, and that's the third law pair. So it's important to keep in mind these third law pairs and try not to get confused if they're acting on the same object. You know, you can have two forces of the same magnitude and opposite in direction acting on the same object, and they don't have to be a third law pair. Okay, so let's look at the problem today. So the problem statement reads, 3 books, A, B, and C, rest on a table. Book A has a weight of 4 newtons, book B a weight of 5 newtons, and book C a weight of 10 newtons. What is the force of book C on book B? Okay, so now that we have the problem read, we see here sort of a simple little picture of what's going on. So what we could do first is mine some information, which is to say they told us the weights. So I'm going to call those FGA, which is equal to 4 newtons. So that's just to say the force of gravity on block A. Similarly, we have this for block B, which is 5 newtons, and then Fg on block C, which is 10 newtons. So let's go ahead and circle this because we'll use this later. So this is just something we'll have to go back to. And then, of course, we can set up our coordinate system for good measure. So let's just go ahead and say that plus y is going up. So we're not too worried about positions, but we want to say that the positive direction is up. So once we have all of that, we now want to do we want to draw our free body diagrams. So we want to draw each of these blocks separately so that we have an understanding of what forces are acting on what block. So instead of drawing these on top of each other, I'm going to draw them side by side. So I'm going to draw block A right here, and then I'm going to draw them with different colors as well. So I'll draw block B over here. And then I will draw block C over here. So the reason we draw them side by side is that way we're very clear about which force is acting on which block, and we don't have to worry about, running out of space here. So in this case, let's start with block A and work our way down. So for block A, we know there will be a force of gravity on block A, and we actually know the amount, so that's nice. So that's one force. And for block A, the only other force that's going to act is going to be a normal force. So we know there will be a normal force on A. And so now, instead of just leaving this as the normal force, I'm going to rewrite this in the spirit of Newton's third law of pairs. I'm going to rewrite this as the force of block B on block A, because that's really what's giving us a normal force. It's the fact that book B does not want book A to go through it, so we have this as force of B on A. And I'm going to use the words block and book interchangeably. They're really the same thing here. So the normal force is actually the force of book B on book A. And so again, we'll use that in a second, but let's now move on to book B. So for this book, we have, of course, a normal force pulling down, which is just going to be force of gravity on book B. And then we also have a normal force here, which is going to be F normal B. So this will be, again, similarly to before, this will be equal to F of book C on book B. And that's just to say in the diagram here, book C is really what's giving book B its normal force. So these are our two forces here, but we actually have a third one that we can't forget about, which is the fact that book A is also sitting on top of book B. So it's going to push down on book B. And so what we'll call that one is going to be force of block A on block B. So again, we're being very clear with which forces are acting on what. So this is force of A on B. And at this moment, I'm actually going to take this moment to realize how these two forces should be related. So we see that this is force of book B on book A, and this is force of book A on book B. And so really, these are a third law pair. A pushes on B, and so B pushes back on A. And so one thing we know, which we can use right away, is that F of B on A, the magnitude of this must be equal to the magnitude of force A on B. And that's just to say if it's a third law pair, they must be equal in magnitude. So that's good, and that'll come in handy. So now let's move on to C, and really this is going to be a similar idea to book B, which is we will have gravitational force on C, and then we'll have a force from book B pushing down on force on book C, which will just be equal to force of book B on book C, and then again we will have normal on C, which will be equal to force of the ground. So in this instance, what's actually pushing up is the ground, and that'll be on block C. So again, being very clear about what's pushing on what, we now have all of our free body diagrams drawn, and we can sort of move on to the next step. And so that's going to be, now we want to realize this is in equilibrium. So Newton's first law applies. So in Newton's first law, we're told that the sum of the forces is going to be equal to 0. So that means that for each of these diagrams separately, the sum of the forces must be equal to 0. So we're going to look at each block separately. So let's start with block A. And block A, there's only two forces, and so we see F of B on A is in the positive direction. So basically, F of B on A must be equal to F of G on A. And so I'm getting that by basically saying F of B on A minus F of G on A must be equal to 0. That's our sum. But I'm going to sort of skip that step and just write, we know that there's only two, they're going to oppose each other. So F of B on A must be equal to FGA. Okay, so that's for book B. So let's go ahead, or book A, sorry. So let's go ahead and move down to book B. So for book B, we see the positive direction is going to be FC on B. And then that's going to be equal to these two forces added together. So that should be equal to FGC plus F of, this should be F of GB plus F of A on B. FA on B. So that's just saying these vectors must cancel each other out, so there's no net force. So we'll do the same thing now for book C. And so here we have F of ground on C is equal to FGC plus FB on C. Okay, so these are the three books, and these are our three equations. So now we have one piece of information we haven't used yet, which is that the third law pairs are equal and opposite. So that means that the magnitude of each of those pairs must be the same. So we see here we have f book B on A and we have f of book A on B. So these two are going to be the same exact magnitude. So when we write this equation, as soon as we solve for B on A, we can plug that right into A on B because they're the same size. So in this problem, it asks us for the force of book C on book B particularly. So we're going to look at this middle equation. So I'll use green for that. So we want to solve for FC on B. So I'll do that down here. So we want FC on B. And we see that that's going to be equal to F of gravity on B, which we already have right here, is 5 newtons. And then it's plus F of A on B, which we don't know right away, but again, we know that's the third law pair of F of B on A, and that we see is equal to the force of gravity on A. So that is equal to 4 newtons. So we can sort of just infer from the line above it this force right here. And so now we have just 5 plus 4. So this will give us a final answer that the force of book C on book B must be equal to 9 newtons. Okay, so let's now real quick review what we just did. We first drew our free body diagrams, and we drew them separately to ensure that we were very clear about which forces acted on which bodies. And then we also wrote down the normal forces as the force of some block on another block to be, again, very clear. Then we used the fact that this was in equilibrium. So we wrote down that the sum of the forces on each block had to be 0. And then taking into note that some of the third law pairs equaled each other, we were allowed to solve through for our desired force. Okay, so I hope this video helped you understand a little bit more about Newton's third law. It's probably the most misunderstood of Newton's laws, and so it's going to be important moving forward that you really understand where everything's coming from. So if you guys have any comments on any of these videos, please leave them under the Videos tab on TED. There should be a survey you can fill out. Thanks for watching.